Hello, everyone, and welcome to Geologic Time. This is great. This is one of my favorite lectures, just because it's just so dang interesting. If you are interested in learning a bit more about the things we're going to talk about today, there's a new book out by a woman named Marcia. Oh boy, good luck with that last name. And called Timefulness, how thinking like a geologist can help save the world. And it's a really good book about geologic time, a lot of the principles we're going to talk about here today, but then also how our perceptions of time sometimes keep us from solving problems. And we think we have plenty of time when we really might not. And so it's a really good book. It's not terribly thick. It's very well written. If you're interested in this kind of thing, if you find yourself at the end of this lecture going, I'd really like to learn more about that, check out that book. And if you want, get back with me and I can recommend even more books. So we want to begin our discussion of geologic time with the idea of uniformitarianism, which I'm just going to call uniformity because it's easier to say. Um, and this is something that I don't know, just about every geology class I ever took, and I took a bunch of them. At some point or another, the professor is going to stand up and they're going to talk about uniformity, and it's important, but it might not be, well, no, it's important, but it is not unique to geology, is I guess what I should say. So uniformity is just the idea that the processes happening in the past are the same as those operating in the present. Okay, that kind of seems obvious. People like to sum it up in various ways. Some people like to say the present is the key to the past. That's okay. I like saying, look, the rules don't change, right? The rules that underlie everything, the kind of the laws of chemistry and physics, that most fundamentally govern the universe, don't change, right? We don't call off the rules. What seems kind of obvious, really, this idea was first put out there by a geologist named Hutton. And Hutton was a great geologist, but a terrible writer. And everyone kind of looked at him and went, "Oh, okay, what do you mean here?" It was popularized a bit later by the guy you see here. I should really get a picture of Hutton too, because he was really a great geologist. But anyway, this guy, Charles Lyell, he was a good friend of Charles Darwin's, although older. And he actually used this principle to found the science of geology with a book that he wrote called Principles of Geology. And it was really the first modern book on geology. It would have been written in probably, I want to say, the 1850s. I don't know. I'd have to look at my copy and see, and I don't have it with me. But anyway, he was really the first modern geologist. And so, okay. But why are geologists so explicit about this, right? Because, you take a geology class or you hang out around geologists, and some point someone's going to say uniformity. They just are, because, it's the founding principle of our science. But it is universal. Everyone believes in uniformity. I mean, you don't wake up in the morning wondering whether or not there's going to be gravity, right? No, of course there's going to be gravity. There was gravity when you went to sleep. There's gravity when you wake up. There will always be gravity, and it always works the same, right? If a historian, for example, is finding evidence that in a particular battle cannonballs were flying further than they think they should, right? One of the ideas is not, well, maybe gravity worked differently back in the Civil War. No, right? No, there's something about the technology of the cannon or the cannonball that you're not understanding. And so, yeah, right, we don't call off the rules. and no one does, right? And I know I'm going on about this. I'm sorry, I always do. But when you take like a chemistry class, right, the professor doesn't say, well, here's the ideal gas law, right? PV equals nRT, and oh, by the way, 100 years ago, PV still equaled nRT, and since the universe began, PV. I mean, no, you assume this. Everyone assumes this. Okay, so why are geologists in particular so very explicit about this? Well, it's because of this guy, Bishop Ussher of the Anglican Church of England back in, I don't know, I think maybe the 1400s, 1500s. I honestly don't know. James Ussher. Ussher pulled out his Bible and he said, I'm going to figure out how old the earth is. And he started when Jesus was crucified, and I believe he was 33 years old. And so he starts there, and he just starts flipping backward and adding up numbers. Make some assumptions here or there, fills in some gaps, because let's face it, the Bible's not really meant to be used this way, but nevertheless, gets back to the beginning and gets a date of about 6,000 years. And there are people, and maybe you're one of them, and I have no interest in changing anyone's mind about this, but there are people who do believe the earth is 6,000 years old, as a result of James Ussher's use of the Bible that way. Well, and he was not the only person doing that, by the way. Isaac Newton did that. Who else? Lots of people were doing this because the Bible at that time was considered the authoritative source for pretty much everything. So along come a bunch of geologists, and they're like, look, if we're not going to call off the rules, 6,000 years isn't really enough time to get anything done, right? Let me show you something here. Let me do this. Okay, so this is some rock on the coast of Portugal. Really dramatic looking rock. And we can see a person here for scale. So it's big. Okay, and you can see that it's been tilted. It's been bent like this, and we'll talk more about this in the next lecture on deformation. It's been eroded flat, and then there's been more rock deposited on top of it. So if we think about what it's going to take rationally to get this rock like this. Now we are assuming that God's not going to miracle those rocks into place, right? That's but that's, once again, that's calling off the rules, right? This is why uniformity is so important to geologists. If you don't call off the rules, then everything takes a very, very long time. Right, if we think about this, first I've got to deposit all this sedimentary rock, and that's going to happen underwater, really, most likely. Then I'm going to have to deform this sedimentary rock and make these folds. Then I'm going to have to lower sea level and erode all this down to this surface right here. Then I'm going to have to raise sea, and who knows how long that's going to take and how much of a gap there is there. We'll talk about those later on. Then, we're going to have to raise sea level again and deposit this rock on top of all this. Then we're going to have to erode all that down. That's going to take a long time. I mean, that's going to take a very long time. There is no way for the earth to be 6,000 years old and for us to not at some point call off the rules, right? I mean, if we just stick with the laws of chemistry and physics and the rates of processes that we know, the earth is going to get very, very old. And this is what Lyell was saying, right? Somehow this slide ended up in the wrong place, so I'm going to have to go back too. But this is what Charles Lyell was saying, right? Is that, look, if we're going to be scientists, we're not going to call off the rules, right? You don't do that. That's kind of almost the whole point of science, right? It's that you don't just miracle things into place. If you're not going to do that, the earth gets very old. Now, at that time in the mid 1800s, they had no idea how old. I mean, they're like, Darwin at one point was like, maybe a million years old, and everyone was like, no, you're crazy, and he's like, yeah, maybe I am. I mean, yeah. So that's why it is so important for geologists, right? This idea of uniformity, because as we, developed as a science, right away we started pushing back against a lot of religious people in terms of how old the earth was and where did it come from and how did it form and all this kind of stuff. So let me just say this before I go on too much, but you know this is the lecture where I kind of explicitly start kind of pushing against some people's religion. And I also know some very good religious books that address a lot of these kinds of doubts and things like that. So if you are interested in reading something from a religious point of view about this kind of thing, I can recommend a couple of really good books on that side of things too. Look, I have no interest in changing anyone's mind about anything. Okay, if you believe the Earth is 6,000 years old or whatever, go for it. I'm not. We're not going to have some sort of debate. I'm not here to change anyone's mind. I'm just here to teach the science. And the science is we don't call off the rules, and the rules of science don't change. And if you don't change the rules of science, the Earth is very old, and we have lines of evidence from several different directions about that. So anyway, when geologists think about time, there's two different things that we think about. This is the most boring slide ever. I should have added a picture or something to it. But there's two different things that we're dealing with. The first is relative time. Relative time is working out a sequence of events, right? And that's what I did here, right? When I said, okay, look, first we deposited this rock, then we tilted it, then at some point sea level fell, and then we eroded this surface flat, and then sea level rose, and we put more rock on top of it, and then sea level falls again, and we erode down to the surface today, right? That's a sequence of events. You'll notice at no point did I say, and the rock is this many years old, right? Never said that. Don't know that. Can't tell that from the picture. Okay, I'm sure someone has gone in there and worked that out, but I don't know what it is. Okay, that is what we call relative dating or relative time, right? Just working out a sequence of events, right? What happened? What happened? What happened? What happened? What happened? You can do that from a picture. Okay, like I said, I'd never been to Portugal, did not take that picture, just found it on the internet, thought it was really cool. Okay, absolute dating is looking at this and going, okay, how old's the rock, right? Like it's 200 million years old or 150 or whatever, however old it is. How old is the rock? That is absolute dating or absolute time. They are related, but they're different, right? Relative dating, we just work out a sequence of events. Absolute dating, we tell how old the rock is. And the techniques for doing this are different for each one. So we did relative dating first as geologists. And so we're going to do relative dating first in here. And to do this, there's a very important scientist who we want to talk a little bit about, Will Smith. Okay, yeah, not that Will Smith. Sorry, I always make that joke. Sorry. Anyway, this Will Smith. Will Smith was a great geologist. He was the first to develop the principles that we're about to talk about and apply them practically in a number of ways. And in particular, he was the first to make a geologic map of England, where he lived, which makes it the first geologic map of anywhere. And there is a really good book. I'm going to go ahead and put links to these books on my courses. So by the time you're watching this, there will be links to Marcia, whatever her last name is, her book. And then there's another book called The Map That Changed the World. And it's about Will Smith and his map. Will Smith was a like I said, a great geologist, but he was also firmly middle class to even lower middle class in England, which means he didn't get a whole lot of respect. And at a time when English geology was, old white dudes sitting in overstuffed leather chairs, sitting around fireplaces, smoking cigars and drinking brandy, and speculating as to what the geology must be like out there. Will Smith was actually out there literally digging trenches. Will Smith had to support himself. He did not come from a rich family, needed a job, basically. Okay. And so what he came to was digging barge canals, right? He was living during the first industrial revolution in England, and the coal is in the north of England, and the factories are in the south of England, right? So, best way to get the coal to the factory is by barge, not by train, by barge. Okay, a big flat boat. And barges require canals. And Will Smith was a genius at moving water. Okay, and you're going, come on, that's not hard. Yes, it is hard. It's not hard in Florida. Florida's flat. You dig a long hole and there's a barge canal, right? No, the United Kingdom, they got hills and mountains and things, and if you need to get your coal from point A to point B, Will Smith is your man. He's going to dig you a barge canal that will do that, and but as he was digging up England, he was paying attention to the rocks, right? He's a geologist, right, and an engineer, and so he's paying attention to the rocks, and he works a lot of this stuff out. He's also paying attention to the fossils. He had the best fossil collection in the UK, I believe, at the time. I mean, it's amazing, his fossil collection, which still exists to this day, by the way. And so he drew this map, and it was promptly stolen by everybody, and no one gave him credit. And he was just during most of his life, he was just not respected nearly as much as he should have been. He actually spent time in prison because he couldn't pay his debts. His friends had to get him out of prison. It was just he led a very difficult life. It was only very late in his life that his work was finally recognized, and the king gave him a pension, and he was able to live out his life in comfort at last. But for him, it was a long, hard struggle. The book is called the what was it the no the I'm conflating those two titles. I want to say the map that saved the world. It's not that. It's Will Smith and the map that changed the world. I'll put a link to it. If you do buy it, buy the hard copy, because the dust cover of the hard copy is the map. Right, you unfold it from around the book, and there is Will Smith's map. It's really very cool. But he instituted a lot of the things that we still do. See how he's colored the rock units in different colors? We still do that today on maps. He did a really cool thing that we don't do. He would color the bottom of the rock unit darker, and it would get lighter as it went up. We don't do that still today, but it's a good technique. It works, it helps you see really clearly what's going on. The other thing Will Smith would do is he would take cross sections across the map, right? He would say, look, if you walk from here to here on, from wherever to wherever on the map, turn it sideways. This is what it looks like, right? And we've been doing this all semester long, right? When we did plate tectonics, all semester long, we've been turning the Earth sideways and looking at it from the side. Will Smith was the first person to do that. So really, very, very pioneering guy who was really only recognized very late in his life as being an absolute genius geologist. He really was. So what are these ideas? Hold on, I need a sip of water. What are these ideas? Well, they're actually not difficult. They're kind of just common sense. It's just that common sense has a way sometimes of ganging up on you and making your life difficult. But they really are just common sense, and I'm not terribly fond of the words common sense because, I don't know, they imply something weird. But anyway, here we go. Sorry. Okay. The principle of superposition, right? If I have a sequence of undisturbed sedimentary rock, the older rock will be on the bottom, the younger rock will be on the top. Okay, now, and now there's important word. There's two important words here, and I bolded them: undisturbed and sedimentary. Undisturbed is important because tectonically, rock absolutely can be flipped over, right? If I go back real quick and we just look at this, right? It doesn't take much at all to get to the idea that that thing's vertical. If I just rolled that over a little bit more, it would be upside down. Okay, it is not difficult at all to flip rock upside down. Okay, so undisturbed is important, right? Or at least upright. Okay, is important. The other important thing is sedimentary. This does not work for igneous or metamorphic rock, right? Because if we think about how sedimentary rock is deposited, the next sedimentary rock is put on top of the previous sedimentary rock, right? If I lay down a layer of sandstone, the next sedimentary rock goes on top of that sandstone, right? There's no way to push a limestone underneath that sandstone. That's not going to happen. That limestone has to go on top. And then the next sedimentary rock has to go on top of that and has to go on top of that, etc., etc. Okay? Now, I can absolutely, though, push some igneous rock up underneath it. Where I could have a whole bunch of sedimentary rock sitting on top of an igneous rock, and whether that igneous rock is older or younger is going to depend on some other stuff that we'll talk about later on. Okay, so once again, undisturbed, or at least you can tell which direction should be up. Okay, and sedimentary. Once you do that, older rocks on the bottom, younger rocks on the top. Okay, let's take a look. So here's like a drawing of the Grand Canyon, right? And so the Grand Canyon is nice because the upper parts of it anyway are sedimentary, and it's pretty flat. Okay, and so this rock down here is older, youngest as I move up. The youngest rock out there is the Kaibab limestone. Okay, I can show you an actual picture of it, right? And so yeah, right, older rock is down here, younger rock is up here. Simple enough. Okay. Here's the horseshoe. Let's see. This is the Badlands in Alberta. This is the Horseshoe Canyon Formation. Lots of dinosaurs out here. And once again, we'll talk about original horizontality. But first of all, we can do superposition out here too, right? Older rock is on the bottom, younger as you work your way up. Okay. Now, original horizontality just says, look, right? Sedimentary rock is originally deposited flat or horizontally, right? So if it's not flat, something had to happen to make it not flat. Okay, and that's an event. So once again, our goal here is to work out a sequence of events. Okay, sedimentary rock is originally deposited flat, and if it's not flat, something made it not flat, right? There's got to be some sort of tectonic deformation out there, right? Here's, I don't know where this is. Where is that? It's really pretty. That looks like it could be the Grand Canyon. That's the red wall, maybe? I think that might be the Grand Canyon. I don't know. Yeah, anyway, pretty rock. And so two things we can tell. It's sedimentary, so we can tell, okay, yeah, this rock down here is going to be older than this rock up here, right? That does look like the Kaibab. So anyway, So superposition tells us older rock down here, younger rock up here. Okay, original horizontality tells us, yeah, this rock is flat. It was deposited originally flat, so there hasn't been any tectonic deformation, right? Original horizontality is most important to when the rock's not flat. Right here we have some chevron folds, some rock that's been really heavily deformed with these very tight folds. Okay, and once again, it doesn't take much to see this going over just a few more degrees and being upside down. Okay, so when we see rock that looks like this, we say to ourselves, okay, something deformed this rock, right? Something in my accounting of what happened out here geologically has to include some tectonic deformation. Okay. Another thing that and once again, I know this all just seems like common sense, but it gets there after a while. Okay. Another thing, oh, did I go 2 slides? Let me see. Yeah, I did. Another thing is something called lateral continuity. For example, if you go to the Grand Canyon, the youngest rock out there is the Kaibab limestone. And you can see the Kaibab limestone on both sides of the canyon. Okay, you can see a lot of rocks on both sides of the canyon, right? Lateral continuity just tells us that those rocks used to be continuous, right? That erosion is what's separating them, right? They were not deposited a little bit over here and then a little bit over there. Right? No, no, no. Right? Those rocks are the same, and so you can see here that you got a bunch of layers being. Let me switch to my little laser pointer here, just so maybe we can see a little bit better. So you got a bunch of layers deposited over here, or rather along a very very long continuous area, and then later on sea level falls, and maybe you carve a canyon. Right, the principle of lateral continuity tells us that this rock and this rock are the same rock, right? And this rock and this rock and that rock and that rock, etc., etc., right? And so if we look at the Grand Canyon, don't sit on the edge of a cliff like that. Good grief! But anyway, you got a rock unit up here, the Kaibab limestone. You got a Kaibab limestone over here, right? They weren't deposited a little bit over here and a little bit over there. They were deposited continuously, right? And then subsequently, the Colorado River cuts down and separates the rock, right? Lateral continuity is what allows us to correlate rocks, and we'll talk more about correlation later on. Places like the Grand Canyon, it's kind of trivial. It's like, well, of course they are. Of course, yeah. If I want to say, a rock over here in West Virginia, a coal is the same coal as you find, in the north of England. Ooh, now we're talking. Right? now that's kind of a lot more interesting. So and we'll talk more about that when we talk about correlation here in just a little bit. One of the most interesting and useful principles is the principle of cross-cutting relationships. And this is just the idea, and once again, it's just common sense, but this one really does get complicated sometimes. The idea is that if I have a fault or an igneous intrusion cutting across another rock, it is younger than the rock it cuts. Okay, so if I have a fault cutting across some rock, first the rock, then the fault. Right, you can't fault something that's not there. Right, here's a little drawing I did. We've got a shaly sandstone down here. We got a coal bed with root casts underneath it. We've got a cross-bedded sandstone with conglomerates. That's probably a river. We got some limestone. We got a shale. We got a sandstone. Right, all these little symbols mean something. And so, if I'm working out a sequence of events, I'm going to go, okay, well, first this, then that, right? Superposition tells me all this is sedimentary rock, older rocks on the bottom, younger rocks on the top. So first this, then that, then that, then that, then that, then that, then the fault, right? The fault has to happen after you deposit the rock. So first the rock, then the fault, right? Here's one in the real world, right? First the rock, then the fault. Okay, if we're thinking about igneous intrusions, here's some what is that? Looks like a quartzite with some looks like mafic basalt-like rock, intruded into it. Right, this is younger, this is older. Right, first the rock, then the intrusion. Right, first the country rock or the surrounding rock, then the intrusion. Right, here's some more. Here's some faults in the Kingman Tuff, which is this is a great picture. I love this picture for a number of reasons. First of all, you can clearly see the faulting, but see these lenses of what look like conglomerate. They are conglomerate. Those are stream beds. That's a stream bed. There's a stream bed. Here's another stream bed up here, almost out of the picture. This is what stream beds look like in the fossil record. Remember, or in the rock record. Remember. When we were talking about sedimentary rocks, I said Conglomerates form in rivers or streams, right? Well, when you see a whole Lindsay conglomerate like that, that used to be a stream running through all of this volcanic ash. But once again, if we're looking at, sorry, hold on. If we're looking at sequences of events, first the rock, then the fault, right? And it seems like common sense, but I'm going to show you how this can really kind of gang up on you here in a minute. Okay, so what about intrusions? Well, here's some intrusions, right? So if I look here, we've got the surrounding rock, we've got the light pink rock, and the dark pink rock. Well, the dark pink rock cuts everything. So it's got to be the youngest, right? The light pink rock cuts the dark rock, but not the dark pink rock. So that one's in the middle, and then this is the oldest, right? So if I'm working out a sequence of events, first the dark rock, then the light pink rock intrudes, then the dark pink rock intrudes, right? And so you can work out, you don't know how old they are, not yet. But what we know is older, younger, youngest, right? Same thing over here, older, right? Younger, youngest, right? The big thick one cuts through everything, right? So that's got to be the youngest, right? Same thing here. We've got the deposition of all this sedimentary rock, and then this intrusion here, and then that intrusion there. And if we really want to go there, that fault right there, I can't tell if that's a fault or a joint or a crack or what, but it's cutting everything, so it's got to be younger than all the other stuff, right? Here we'll learn next time that this is called a normal fault. And so, once again, two faults, one there and one there, but they're obviously related, dropping down this wedge. We'll look at this picture again next lecture. But you can see first the rock, then the faults, right? You can't fault nothing, okay? So the rock has to be there first. Here's another little fault cutting across some looks like granite, but you can see a little intrusion here that's been cut by this fault. We'll learn next time this is called a right lateral fault. So first the granite, or whatever that is, looks like granite, then the intrusion, then the fault, right? So here's another thing though. This is the Bishop Tuff. And you can see that you got a tuff here, you got a bunch of volcanic ash cut by faults, but with a lava flow on top of it. Notice though that the faults don't extend, they don't cut the lava flow, right? So faults are younger than what they cut, but they're older than what they don't cut, right? And so let me show you. So there's the fault there, and there's the base of that lava flow uncut by the fault. So if I'm working out a sequence of events here, I say, okay, first all this ash getting turned into a tuff, then it gets faulted, then the lava flow happens, right? If this fault had extended up in here and cut the lava flow, then I'd be going, okay, first all the ash, then the lava flow, then the fault. But it doesn't. It stops at the bottom of that lava flow. So first the ash, then the fault, then the lava flow. Right, here's a fun one. This is you can see a big igneous intrusion here, and so it's got to be younger than all this rock that it intrudes into. And so first all this rock, then this big old igneous intrusion here, and you can see that it's faulted in a kind of faulted. Yeah, there's a fault. There's a good fault. It's faulted in a couple of places that would have had to have happened after it was intruded. So geologists in the field, one of the first things that we do is we go in and we work out what's in the subsurface, right? Look, if all you do is walk along this rock, you're going to be in the same rock all day long. You're not going to know about anything, right? So what we do is we look for stream cuts, look for railroad cuts, look for road cuts, look for anything that'll give you a look at that rock from the side, right? And once you get that worked out, then you can work out a sequence of events. But you need to know what it looks like from the side. If you have to, drill it. But drilling, that doesn't tell. It's going to be a real pain in the neck. It's expensive. No, find some road cuts, find some stream cuts. Hopefully maybe your rock is tilted so you can walk over it on the surface. But in this case, it's not. Like I said, if all you did was walk across this rock, you're going to get that fault. And that's all. That's all of this, you're not going to know about any of this. So find yourself some some cuts that show you what it looks like from the side. Then you can work it out, right? And so, if we look at this, I can see three igneous bodies. I got a batholith here, I've got a dike and sill complex here, and I got another dike here. Well, that cuts across that. So that needs to be younger than that, right? This cuts across that. So this needs to be younger than that. So if I'm just thinking about the igneous complex out here, first the batholith, then dike and sill complex B, and then dike A, right? Because this cuts that and that cuts that. So there's that. Now, if we add in the sedimentary stuff, and we got a couple faults we want to think about. So once again, superposition tells us older's on the bottom, younger's on the top. So first this, then this, then this, then this, then this. And look at this fault. This fault is like that one we saw in the Bishop Tuff, right? Where it cuts that rock, but it doesn't cut that rock. So after I deposit this rock, then I fault it, right? And then I deposit this green rock on top of it, uncut by the fault. Right now, we know that this batholith cuts across everything, so that's going to be one of the last things that happens. So then I can deposit the rest of this rock. Then I can come over here and fault it. Right, that fault doesn't cut that batholith, so you can see how the common sense is ganging up on you. Now, and this is just one out of a textbook. Imagine a real life one, right? But the fault doesn't cut the batholith, so first the fault, then the batholith, then dike and sill complex B, then dike A, and you're done. You got it, right? First this sedimentary rock, then the fault, then the rest of the sedimentary rock, then that fault, then that batholith, that dike sill complex, that dike, and boom, you're done, right? Yeah, right. It's, as you take these one at a time, you're like, oh, okay, yeah, I get that. You put them all together and it gets more complicated. Now, here's the good news. In class, you're not gonna have to do that. I might just give you a stupid, simple little look. Here's some fault cutting, some rock, which is older, which is younger. Okay, I'm not gonna give you something like this. If you're in a lab, you're gonna do this. Okay, so just kind of, take a breath. It'll be fine. So there's a couple other things though that'll help us out too. Inclusions. An inclusion is a piece of one rock inside of another rock, right? And so here you can see, here's an inclusion of something I don't even know. God, what is that? That looks like a schist, doesn't it? I think those might be micas. Anyway, piece of this rock inside of this rock. This rock is older. This rock is younger. Okay, the inclusion is older than the rock around it. This rock has to exist before it can be included in this rock. And I just read the caption. If that's enchanted rock, then that is granite, and that is a schist. But anyway, here's another one. And so you can see here. Here's some rock around it. There's an inclusion, looks like a basalt. This has to exist before it can be included in the surrounding rock, right? And so, if we think about this kind of diagrammatically, we can see here, like if I have an igneous intrusion here, and then I've got pieces, sometimes inclusions are called xenoliths. Xeno meaning foreign and lith meaning rock. So foreign rocks, okay? So if I look at this situation here, there's a very real question about what order did all of this happen in? And if I look at this, I can see pieces of this surrounding schist, which is what those squiggly lines mean, or high, intermediate to high grade metamorphic rock. I can see that inside the granite, right? That means that had to be there before the granite. And then we can also see pieces of the granite inside of this shale up here, and also pieces of that schist in that shale. And so what we know then is that this basement rock, this country rock, this surrounding schist here was sitting there. That granite intruded up into it. And broke off pieces of it into it, so we know that this has to be old. There we go. This has to be older. That has to be younger. Intruded into it, and then sat there for a while and was eroded. and pieces of the granite broke off into the shale, which tells us that between the granite and the shale, the granite needs to be older. And I know by now you're rolling your eyes because you're like, oh my gosh. But this is the kind of stuff that geologists have to sort out. You need to know, okay, what is the sequence of events here? Let me give you a more limited and maybe better example. Let's just say that you have a granite sitting up against a sandstone. That's right now. That's all I know. So I can think of two scenarios, right? The first, let's call the Stone Mountain scenario, right? The granite is sitting out there in the open, and sea level rises, and covers it with a sandstone. So there's one scenario, right? The other scenario is that the sandstone is sitting there, and the granite comes up underneath it. Okay, so those are two very, very different scenarios, and you don't want to get them wrong, right? You don't want to be talking about sea level getting jacked up and down to cover that granite when it didn't. Likewise, you don't want to miss sea level getting jacked up and down to cover the granite, and so yeah, you don't want to get that wrong. So what do? Look for inclusions, right? If the granite, like Stone Mountain, was sitting there and sea level rose to put that sandstone on top of it, you're going to get pieces of that granite in that sandstone, right? You go to Stone Mountain, there's pieces of granite laying around all over the place, right? Yeah, you're going to get those pieces incorporated in that sandstone. So this scenario here with the granite and the sandstone tells me the granite was sitting there, the sandstone was deposited later on. On the other hand, if the sandstone is sitting there, then and the granite comes up underneath it, pieces of that sandstone are going to break off into that granite. And so you're going to have, xenoliths or inclusions of sandstone in granite, right? So take your time, get it right, find the inclusions, okay? If there's pieces of sandstone in your granite, that means the sandstone is older and the granite came up underneath it. If there's pieces of granite in your sandstone, that means that the granite is older, was sitting there when the sandstone was deposited on top of it. Don't get it wrong, right? You get that wrong, you're going to have to go find something to do other than be a geologist, okay? Because it's not hard, pretty obvious to a geologist, and you don't want to get that wrong. You don't want to be jacking sea level up and down if it didn't get jacked up and down, but at the same time, you don't want to miss it if it went up and down, right? And so these are two very, very different scenarios that can be sorted out just by looking for some inclusions. That's all it takes, okay? Another thing, let me just mention this real quick. You might have, we talked about metamorphism. We talked about contact metamorphism. And so, yeah, if this granite comes up under this sandstone, you would expect to see contact metamorphism along here where that hot granite came up against that sandstone. It's really easy to miss contact metamorphism. It's a pretty rare thing. That granite will need to be really dang hot, and sometimes it happens, sometimes it doesn't. So, contact metamorphism might be a little bit overrated sometimes. You don't always see it, and it's not even always there. So, find the inclusions. They're a lot more reliable. Okay, so, there's another thing that happens that we want to talk about. And that is an unconformity. Now, I'm going to give you 3 different kinds of unconformity. On the review sheet, I cut them I just ask what an unconformity is, right? What an unconformity is a gap in the rock record, right? Here, back to Portugal, right? This is an unconformity right here, right? This is a time where we didn't have any deposition of rock at this particular location, right? This is an erosion surface, right? You've all seen an erosion surface. I promise you, every single one of you has seen an erosion surface. Every time you walk around outside, you're walking on an erosion surface. You're walking on a future unconformity. If sea level rises and inundates Florida, and let's face it, that's probably going to happen, you're going to have some missing time there. Let me show you what I mean. So if we just stick with Florida, if we go up north on 19, past Homosassa Springs, and this is 19 crossing right here at the Florida Barge Canal. The Florida Barge Canal cuts through some of the oldest rock in Florida. It is about 40 million years old. If I was standing in front of you, I would hold up a piece of it that I collected some time ago. Now, let's imagine though, okay, so that's exposed on the ground, right? Let's just say, let's think over here, okay? Now, if sea level rises, there's a 40 million year gap there, where we don't have any rock for at that location. Okay, let's do it again. Let's go up to Canada. This is the Canadian Badlands in Alberta. The Royal Tyrrell Museum is right in the middle of this rock formation. It's the Horseshoe Canyon Formation. It is about 70 million years old. So that rock that I'm standing on there when I took that picture is 70 million years old. If I were to raise sea level and flood this, there would be a 70 million year gap there, right? We would be missing the extinction of the dinosaurs, and then the rise of the mammals and the entire Cenozoic, right, up until now, would be, missing there. And in fact, there is an unconformity back here called a disconformity. I'll tell you about that here in just one second. But see how you got rock here, but you kind of got green grassy stuff here. Okay, this is the Horseshoe Canyon Formation. That is 70 million years old. This is glacial sediment from the last glacial interval that is about 10,000 years old, right? So you do actually have an unconformity here between the Horseshoe Canyon Formation down here and the glacial outwash here. I don't know what it's the glacial outwash. I don't know if it has a name or not. But anyway, so there is actually already an unconformity here, right? But if we if we raise sea level and put it here, we've still got unconformity over here too, etc. Right? We can do it. We can do it a couple more times here. Let's go to the Canadian Shield. I did not take this photograph. I've never been to the Canadian Shield, but I would love to. This rock is a couple billion years old exposed at the surface, right? Okay, so if I raise sea level, now I'm missing a couple billion years worth of time. I'm missing, the entire history of multicellular life here. I'm missing a lot. One more time, and then we'll be done with this particular little exercise. This is these are some banded iron formations in Australia. I wish I had taken this photo, but I hadn't. I've got some of this rock, but this rock is like 3-4 billion years old. This is some of the oldest rock on the planet. If I raise sea level, now I'm missing, I'm missing everything. Well, not missing everything, but I'm missing a lot. I'm missing an awful lot, right? That's what an unconformity is. It is a gap in the rock record, right? It is a location where there was erosion and then subsequent deposition, leaving you with a gap in the rock record. Okay, now, there's a few different kinds for the test. I'm not worried about the kinds, but here they are, right? We've been looking at angular unconformities all day, right? It's a gap in the rock record where the rock underneath it is tilted, the rock on top of it is flatline, right? That unconformity in Portugal is an angular unconformity, right? Here's one. I don't know. This is just a picture I found on the internet, but these are bang on easy to see, right? I mean, it's just kind of obvious, right? Here's another one. This is in Sakar Point, Scotland. This is kind of like the angular unconformity. Hutton saw this and kind of used it and realized things were going to take a long time because he realized what had to happen here, right? And we'll talk about that here in a minute. But notice also that this angular unconformity itself has been tilted, right? The rock on top of the angular unconformity has itself been tilted. It's not even flat lying. So if I was to deposit more on this, I would have a weird double angular unconformity thing going on there, which would be really kind of crazy. But anyway, angular unconformity, right? There's one out at the Grand Canyon too. Here's a very shallowly dipping angular unconformity at the bottom of the Grand Canyon. And so, here's how they form, right? You deposit some rock flat, horizontally, original horizontality, etc., right? Warp it upward, give it some uplift, okay? Then erode it flat. Right, I erode it flat, so now I've got a ground surface here, right. Then raise sea level again and deposit some more flat rock on top of it, and sure enough, there's your tilted rock underneath your flat-lying rock with the erosion surface in between them. Here's one over here, with that tilting and etc. Along with angular unconformities, there are disconformities. A disconformity is a gap between parallel layers of sedimentary rock. So imagine this without the uplift, right? Just imagine that I deposited a bunch of rock flat, eroded it down, and then put more rock on top of it, right? That gives you a disconformity, right? Where, you've got a surface here that was an erosion surface with flat rock underneath it and flat rock on top of it, right? These are notoriously difficult to spot. Here's one at the Grand Canyon. Is there anything about that you can just look at it and tell that that's an erosion surface? Okay, no. We have various tricky ways in the field to get this, but it can be tricky. It can be really hard. You can walk right over one and never know it. You have to be paying very careful attention to what's going on. We have some tricks that we can use, but you have to be very careful about paying attention to what's going on. You really do. Disconformities are crafty little buggers. Then there's a nonconformity. A nonconformity is an erosion surface between igneous or metamorphic rock and sedimentary rock. And my message for you today, especially if you're going to go on in geology, is people are unfortunately inclined sometimes to call every single contact between an igneous and a sedimentary rock a nonconformity. That's not true. Okay, now, every contact between metamorphic and sedimentary rock is a nonconformity, right? Look, here we are at the Grand Canyon. Here's the Vishnu schist down here. And then here is, I believe, the Bright Angel shale right on top of it, right next to it, right? We know there has to be an erosion surface there, right? You cannot apply enough heat and pressure to turn this into a schist and leave that as a shale if it was there. Not going to happen. That's going to be schist 2. So what we had to do then was make this into a schist, erode this flat, and then who knows how much later put that on top of it. Right, that has to be much, much younger, and it has to not have been there when that was turned into a schist, or it would be a schist as well. Igneous rocks are a little bit trickier though, right? Because look, not every contact between a sedimentary rock and an igneous rock is an erosion surface, right? Look, this on the left is a nonconformity, right? That is an erosion surface. You are missing who knows how much time between that granite and that sandstone. You could be missing 1 billion years between that granite and that sandstone, okay? This, on the other hand, this is an igneous contact, right? You're not missing any time here. That sandstone there, the granite came up underneath it, right? There's no erosion surface there. Nonconformities and every unconformity in the world is an erosion surface, right? So don't you make the mistake, if you go on in geology, and I know a couple of you are, of assuming that every contact between an igneous rock and a sedimentary rock is a nonconformity. It's not. It needs to be an erosion surface. So nonconformity over here, igneous contact over here, right? Same thing here, right? All these intrusions are igneous contacts, right? They're not non-conformities. They're not unconformable surfaces at all. They're just igneous contacts. We know exactly what happened out here. First that, then that, then that, right? We already worked that out. So, putting all this together, right, and I did this once before, but let me just show you real quick, right, is, if you have a section that looks like this, right, what you want to do is work out the sequence, right? First, you deposit these layers down here flat, right? Then you push that sill in there. They kind of threw a curve at you and threw a sill in there, which you can tell is a sill because it's got little pieces of that sandstone in it. Okay, you know, then we're going to intrude that dike, right? Then we're going to tilt everything. Then we're going to deposit, we're going to erode. Then we're going to deposit more stuff on top of it. Then you end up like that, right? And so work. Here's a funny thing. When geologists do this kind of work, we start at the bottom and go up. We go in the same direction time goes. Archaeologists sometimes have to do the same kind of work. When they do it, they start at the top and go down. It's a really interesting and very odd and very fundamental difference in the way archaeologists think and geologists think. I'm not saying anyone's right or wrong, but when archaeologists and geologists combine to do this kind of work, they have two very different approaches to it, right? A geologist is going to go first unit A, then B, then C, then D, then rather than E, then D, F, and then blah blah blah. An archaeologist is going to go K, J, I, H, G. They're going to start at the top and go down. I was married to an archaeologist for a while, and it didn't work out, and I think that's probably one of the reasons. No, that's not the reason. But anyway, very, very fundamentally different approach to how we do these things. So remember before I said, that the idea this rock over here is the same as this rock over here, the idea of lateral continuity, right? And I said, look, at the Grand Canyon, it's kind of trivial, and it kind of is, but other places it's not, right? You can use this idea of lateral continuity to do something called correlation, right? And what correlation is it's matching rock units across space, and what it lets you do is build up a stratigraphic column where you don't have all that rock at any one place, right? And so, for example, if I'm out here at the Grand Canyon, hooray for the Grand Canyon, okay, it goes, so let me just do it this way. Grand Canyon, okay, another location, Zion National Park, out west, okay, another location, Bryce Canyon, okay. Now, if I look at where these three are, okay, here's the Grand Canyon here in Arizona. Up across the border in southern Utah is Bryce Canyon. And then off here to the west is Zion National Park. Well, if I look at the rocks in each of these places, one of them picks up where the other one leaves off, right? The youngest rock in the Grand Canyon, is here, let's say, either the Kaibab limestone or the Micanopy formation. Those are the two youngest rocks there, right? Well, guess what? You run out of rock, right? And hold on, I'm not sure which one is which. Hold on, let me just see here real quick. Zion. Okay, that's what I thought. Okay, so you run out of rock. Okay, well, what do you do? Well, come over here to Zion, right? At Zion National Park, the Kaibab and the Micanopy are the lowermost units. So lateral continuity tells me that these were once the same rock, and so I can correlate. I can say, okay, this guy, that's the same thing, right? And so I can go up, right? At Zion, you run out with the Navajo sandstone and the Caramel Formation. That's fine, right? Go over here, all right, I gotta check it again. Yeah, go over here to Bryce Canyon. Sorry, Bryce Canyon, where the Navajo and the Carmel are at the bottom of the formation, right? And so now I can work my way all the way from the Tapeta sandstone or even the Vishnu schist at the bottom, all the way up through. Way more rock than I could if I was at any one location, right? And geologists, we do this all the time, right? And it requires very careful work because you want to make sure that this is exactly the same limestone, right? You don't want to be correlated. Well, here's a line. Yeah, there's a limestone over there. If it's not the same one, that's not going to work, right? You want to make sure that, this is the Navajo sandstone. You do a very good, very thorough description of it so that when you find it again over here, you recognize it. Right, and so and there might even be a facies change here, which is a whole other thing. But anyway, so this allows us then to assemble more rock together than we would have in any location, right? And once you do that, then you can start stalking. Then you can, then you find some fossils, and you can start assigning. Ages of this, right? I mean, look, the youngest rock in the Grand Canyon is Permian in age, which means that there's no dinosaurs in the Grand Canyon. It's all too old for there to be dinosaurs in it. It just is. Okay, so if you're a paleontologist and you're looking for dinosaurs in the Grand Canyon, you need to find another job because you suck at being a paleontologist because there's none out there. There's other stuff out there, but there's no dinosaurs out there. If you want dinosaurs, go to Zion. Okay, there are dinosaurs there. Okay, because now we're into the Triassic and the Jurassic, right? But for example, if you're looking for a Tyrannosaurus Rex, no, not going to be there. That's a Cretaceous dinosaur. You need to be up here in Bryce Canyon. Okay, so you can see that we can assemble a much larger stratigraphic column than we would normally have by correlating rock units. Okay, and so now, whereas at any one place you only have this much time, when you put them all together, you got much more time. Now there are unconformities in all these places. So we are missing rock. There are unconformities there, but at least you have that span, and then you find other places and you fill in the gaps. Okay. I'm not gonna put my 5 minutes of break in here, but I'm gonna hit pause for a second, take a little break. You all do the same thing. We're gonna come back. We're gonna talk about biostratigraphy, and we're gonna talk about radiometric dating, and that'll wrap us up. Okay. But let's take a break. It's been almost an hour. Take a break, walk around, get some water, do something else. Okay, I am. Okay, I hope you enjoyed your break. I certainly enjoyed mine. And so, we can date things. We're still on relative dating, right? We're still just on working out a sequence of events, working out which rock is older, which rock is younger. And so, and you can do this also using fossils. And when you do that, it's called biostratigraphy, by the way. This works because of something called the principle of faunal succession. And this is just the idea that not everything lived all the time, right? There is a pattern in the fossil record of things changing. This is not evolution, by the way. Evolution is explaining why things change through time, right? The observation that things change through time is just that, an observation, right? Once you get all the rocks in order, you realize that, if we just use the most simple marker that we all know, dinosaurs, right? There was a time before the non-avian dinosaurs. There was a time, during the non-avian dinosaurs, and there's a time after them, right? And so if you find a Tyrannosaurus fossil, you know that you're in the Cretaceous, right? If you, whatever, right? And you can get very, very detailed with this. You really, truly can. And a lot of times we don't use big fossils that you see, around you and in museums, but a lot of times we use little, what are called microfossils. These little foraminiferas is about the size of a grain of sand. There's another foram that looks like a diatom to me. There's a big old foram, it's agglutinated. Anyway, all these little microfossils, right? You can use these. Now, not every fossil, though, is useful for biostratigraphy. Okay, we have a very particular kind of fossil called an index fossil. It's very useful. Okay, and I'm going to do these bullet points in a little bit different order. Okay, first of all, the fossil needs to have lived for a short time. Okay, you can't, because remember that the ultimate goal here is to figure out how old that rock is, relatively speaking. And so, if something lived, well, okay, here we go, right? This is the inarticulate brachiopod lingula. Here is a fossil lingula over here. Here is a modern lingula here. Do you see the difference between the fossil lingula and the modern lingula? Because I don't. They're virtually the same. These fossils go back to the Ordovician. They go back 400 and something million years old to today. So if you find a lingula in the rock record, good for you, but that does not tell you anything about the age of that rock. It could go from, just a few thousand years to now to hundreds of millions of years old. Not useful for biostratigraphy. Okay. On the other hand, though, if you find this guy, this is Olanellus. This is a trilobite that was very common in the lower Cambrian, about 500-ish million years old, let's say, but we're not to the numbers yet. Lower Cambrian. Okay, if you find an Olanella trilobite, you are in the lower Cambrian. You know this. Okay, those things they went hot and fast. They did not live long, but there were a bunch of them. So they're pretty common in rocks of the lower Cambrian, right? Which brings us to the another bullet point here, right? They do need to be common in the fossil record, right? Useful index fossils are very common. You need to know that if you're in the lower Cambrian in the right environment, odds are you're going to find an Olanella trilobite. It doesn't do you any good if it's very short-lived, but there were only 12 of them. Okay, that's not going to help. Okay, the other thing, ideally, I'm doing my bullet points exactly in reverse, is that you want it to be very geographically widespread, right? It would not do you any good if Olanella trilobites, only lived in the basal Cambrian, are very common in one place. That's not helpful, right? You want it to be pretty geographically widespread so that if I'm in the lower Cambrian, in the United States somewhere, and I'm in the lower Cambrian over in Europe somewhere, odds are I'm going to find an Olanella trilobite, right? You need them to be very, very geographically widespread. So if you have a fossil that is geographically widespread, very common in the fossil record, and lived for a short time, those are very, very useful for doing biostratigraphy, right? For figuring out how old the rock is based on the fossils. And so yeah, we call that, once again, we call that an index fossil, right? Lingula, not an index fossil, okay? Olanellus, awesome index fossil. All right, now, we have some words that we use when we do biostrat. And I'm going to tell them to you, and then I'm going to switch over to my drawing pad and show you how this works. First of all, there's these different kind of zones. And the most basic one is a range zone. That's just the time period that the organism lived in, right? It's like our Olanella trilobite that lived in the basal Cambrian, right? You find that Olanella trilobite, bingo, you're in the bottom of the Cambrian, okay? A concurrent range zone is the time where you have two or more organisms living at the same time. And I'm going to show you in a minute here how this can be very, very helpful in figuring out how old your rock is. Okay. Then we have a first appearance datum, which is that time when an organism first appears in the fossil record, and then a last appearance datum. That's going to be that time horizon when the organism disappears from the fossil record. Okay, so range zones, concurrent range zones, fads, and lads. Okay, I'm going to switch to my drawing board and show you how these things work. Okay, so here we go. So let's think about this a little bit, and let's say that, and really, if you want to be very concrete about this, you can imagine that you are literally looking at a cliff, okay? And so superposition tells us that the older rock is on the bottom, right? I can't write, and the younger rock is on the top, right? Okay, and so time is kind of going this way, right? And you don't have to think about it like this, but you can literally think about like we're looking at a cliff, okay? And so let's say that, different organisms are going to appear and disappear from the fossil record throughout this time. And this could be billions of years, okay? It doesn't need to be 20. In fact, it should not be like 20 years or something weird like that, right? My G looks like a Y. Can I fix it? Ooh, I kind of can. Okay, I can't draw it right under the best of circumstances. So anyway, okay, so a species appears here, right? Okay, so there's the fad, right? There's the first appearance datum, right? And it exists for some time, and then it disappears here, right? So there's the lad, right? There is its last appearance datum. Okay, so this time here, this is the range zone, right? ANGE zone. That's the range zone, right? If it's short enough, then you can use it, right? If like Olanellis, that basal Cambrian trilobite, it has a range zone like that, right, where it's very short lived. So if you find it, you're narrowed down to this much time, not very much time at all, right? If you had something that lived for an even shorter amount of time, it would be even better, etc. Right? That brachiopod we talked about, Lingula, it's like this, right? And if I find that, that's not doing me any good at all. Okay, now. Okay, so range zone is good, right? And the shorter the range zone, the better the fossil is as an index fossil, right? So if this is, maybe this is Olanellis, and I don't know, maybe that's something else, I don't know what. Okay, it doesn't really matter. Okay, so if I find this fossil here, that tells me something about how old the rock is. If I find this fossil here, that tells me something a little bit better about how old the rock is. And if I find this fossil here, that tells me a lot, right? That's pretty dang good. Okay, now so those are range zones, right? And that's just the idea that I find a fossil, I know how old it is, right? But what's a concurrent range zone then? Well, that's where two fossils overlap, right? So let's go up here. Let's say that I have a fossil that has a fad down here and a lad up here, and so it's there's the range zone there. Okay, and what are we up to? This is fossil 4. Okay, fine. Okay, so you find that, you're okay. That's nice. It's not great. It's kind of like that one, right? It's not great. Okay, but let's say that I have another fossil that lived for this long, right? So here we are with fossil 5. Okay, so let's say that, let's see if I make my 5 a 5. Whatever. Anyway, either of these by themselves isn't terribly helpful. Okay, but look at what happens here. If I find both of them, right? If I find 4 and 5, I'm going to try to draw a dotted line here, where both of their range zones are, well, that's pretty good, right? So that's fossil 4 and 5, right? If I find both of them, that narrows it down a lot more. That, right? If 4 tells me this, that's a pretty good stretch of time. 5 tells me this, that's a pretty good stretch of time. 4 and 5, that narrows me down to here, right? That's pretty good, right? And so that's what we mean by a concurrent range zone. Okay, and that's why they're really helpful. So we usually don't go out looking for individual fossils. We usually go out looking for groups of fossils, right? Because they help us narrow down the time a little bit better. Now, if we're fortunate, let me get rid of that right there. So fads and lads are important, and they can be very, very useful. Let me kind of clean this up a little bit. They can be very, very useful because that isn't a stretch of time. That is a very specific time horizon right there where that fossil appears, right? And so if you know when that first appearance datum is and you find it, you're really very well narrowed down. So so what one is that? That's fossil 1. It doesn't matter. It doesn't matter. I sample here, I don't find it. I sample here, I don't find it. I don't find it. I don't find it. I don't find it. Boom, I found it. Go back and sample a little more in here and here and here, a little more here and here, right? So you can narrow that down, right? So you know where that first appearance datum is. And now you have a very good idea about how old that rock is because you found the first appearance datum. Now there's issues with local first appearance data, and global first appearance data, local first appearance. I mean, it's more complicated than that. Everything is more complicated than that, right? But it's still a really good way to narrow down where you are in the rock record, right? Same thing up here with the last appearance datum, right? You got it, 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 you got it. Whoops, you don't have it anymore. Okay, right in here, there's your lad, right? And so if you know when that lad was, you know how old that rock is, right? And so this is biostratigraphy. There are more complicated ways they do this. They have these huge data sets with lots of what they call bugs in them. Oil companies have these huge proprietary data sets they don't let anyone else see. So as they're drilling, they know exactly where they are in the rock record. So I want to show you something that's just kind of fun and maybe interesting that has to do with extinction. And so let me clear this. I'm sure I could push one button and clear everything, but what's the fun of that? Okay, so let's say though that we have organisms appearing and living and disappearing and appearing and living and disappearing, all, kind of, and I've drawn this kind of not randomly, so let's put some down here, and, just things are just cooking along the way they normally do. In the rock record, right? Things show up or live for a while, and then they disappear. And this produces what we would call a background rate of extinction, right? Where things just kind of naturally show up and live and then disappear. And maybe they evolve into something else, or maybe they move out of the neighborhood or whatever. But there's certainly no mass extinction here, right? This is just the normal kind of thing where organisms show up in the rock record and they live for a while and then they go away. Right, nothing to see here. The normal, I accidentally drew some things in a weird pattern there. Let me see if I can get rid of it. Right, this is the normal background rate of extinction, and this might be, several 100 million years, right, worth of rock here, and things just kind of showing up and living, doing their thing, and then they like I said, they go extinct. Okay, so like I said, normal what we call the background rate of extinction. Nothing to see here. Now, let's though take this and expose this rock, and let's make an unconformity. Let's just make a disconformity, right? And so let's erode this rock down to a level, and let's just say that level is right here. Okay, so what I've just done is I've just removed this rock. Okay, so at this particular location, I don't have any of these fossils. Okay, now, so I eroded the rock, and now let's say, so this is kind of for a while, this is the ground surface, right? Where these rocks, these fossils kind of, I don't need to go down to that one. Anyway, so we got the ground surface here. If I push harder, it makes a thicker line, and I haven't really worked all that out yet. But anyway, now let's put more rock on top of it, right? So let's deposit some more rock on top of it. And it may or may not have fossils in it, but that's not important, right? When I put more rock on top of this, and it could be a shale or whatever, okay, suddenly, when I look at the fossil record, it looks like everything went extinct at the same time, when they didn't, right? They lived on, but at this location, you don't have them living on. Suddenly, everything looks like an extinction, right? I just made a quote-unquote extinction event here, right? Extinction, right? I just made an extinction there. It's not an extinction. It's a disconformity. But if you don't know it's a disconformity, it's going to look like everything went extinct right there at the same time. You can make a very sudden looking extinction in the fossil record by making a disconformity. And the interesting thing is, the KT extinction that took out the non-avian dinosaurs, every single section that we have of that event has a disconformity. So, and people sail right past this when they talk about that extinction. They just assume all kinds of things that are simply not in evidence. And so you want to be really, really careful when you're talking about rates of extinction, and make sure that you're not dealing with a disconformity rather than an actual biological event. Okay, I'm going to switch back to my PowerPoint, and we'll talk about a couple other. We'll talk about radiometric dating. I believe is up next. And my mouse is being weird because I got my drawing thing laid down on my tablet. That's why. Okay, here we go. There we go. Be right back, guys. Okay, I'm back, and this is essentially showing you what I just showed you with my drawing tablet, so I'm not going to worry too much about this. It's actually a little bit more confusing than what I just showed you. So anyway, so using the techniques that I just showed you, right? Using Will Smith's relative dating techniques, using faunal succession, right? You get all the rocks in order. Now, here's kind of the way this works, though. Once you get all the rocks in order, you realize that not everything lived all the time, right? And there are definite patterns of organisms, appearing and dying in the fossil record. And once again, we call that faunal succession. And so, once you kind of get the rocks in order, you realize that there's a long time here where there's no obvious fossils, right? We call that the Precambrian, mostly because the first division of the Paleozoic is the Cambrian. So no real obvious fossils. As we work more, we realize that we can divide this up based on various and sundry other things. Life goes back, actually, by the way, back to down around in here, which is kind of interesting. But and then after the Precambrian comes the Phanerozoic. This is the time of obvious, oh, look, a fossil life, right? And so we can kind of expand that out a little bit. Precambrian, Cambrian, Ordovician, Silurian, Devonian, Carboniferous, divided into Mississippi and Pennsylvania. That's the Paleozoic era of primitive life. Huge extinction here. Huge extinction here. 90% of everything on the planet dies, clearing the way for the dinosaurs. The Mesozoic, we have different kinds of things living at different times in the Mesozoic, so we divide that into Triassic, Jurassic, and Cretaceous. There's an extinction here, but it's not that big a deal. No, it's kind of a big deal, but there's an extinction there. And so that clears the way for what we commonly call the age of the quote-unquote mammals, although mammals go back into here pretty far too. But that's the Cenozoic. Because we have more rock, because we have a more detailed fossil record, we can divide it up even more finely in the Tertiary, Quaternary, which we can divide in the Paleogene, Neogene, which we can divide in the Paleocene, Eocene, Oligocene, Miocene, Pliocene, Pleistocene, Holocene, and all these are different kinds of mammals, and then also glacial intervals. There's all kinds of stuff going on in here. Like I said, it's younger rock. We have more of it. We can divide it up more finely, right? And so yeah. So geologists were able to put all these words together. It's kind of a mishmash of a bunch of different systems. The Cambrian is named after the Cambria, England. The Ordovician is named after the ancient Ordovici tribe. And there's different, Mississippian and Pennsylvanian, kind of obvious. And so it's kind of the nomenclature is kind of cobbled together. But there it is. Okay. And yeah, so, using correlation, we're able to kind of piece together the history of life on Earth, because once you get all the rocks in the right order, the faunal succession just jumps out, and it's easy then to subdivide things. Okay, not maybe easy, but easy enough. And so yeah, now, for the longest time, what we didn't have were the numbers, right? These are in millions of years. We didn't know this. Right, so, you would hand a geologist or a paleontologist a rock with a fossil in it, and hopefully it's, enough of an index fossil that they could say, okay, so let's use one we know, right? You hand a paleontologist a rock with an Olenellus in it, and they go, okay, this is basal Cambrian. And you go, okay, how old is that? And they say, basal Cambrian, right? Yeah, so there's a problem. There is absolutely a problem. So, We don't have the years. We don't have the numbers. So how do we get the numbers? Well, that's interesting. A lot of people tried and failed. Lord Kelvin most famously tried and failed, which I like pointing out because Lord Kelvin was kind of a snooty jerk. Charles Darwin's son, whose name escapes me right now, tried and I mean, lots of people tried and failed. Lots of different things. It's going to take an understanding of radioactivity to be able to absolutely or radiometrically date a rock, right? To work out the age in years of the rock. And so, if we think about radiometric dating, it begins with Marie Curie around the turn of the century. She would win two Nobel Prizes, one in 1903 and one in 1911, one in chemistry and one in physics, for her work with radiation. She remains to this day, by the way, the only person to win two Nobel Prizes in two different science fields. Okay, Linus Pauling won two, but one was in chemistry and one was the Nobel Peace Prize. Different. Okay, lots of people won two in chemistry or two in physics or two in medicine or whatever, right? Marie Curie won one in chemistry, one in physics in the early 1900s, y'all. Can you imagine how good she must have been? And she was amazing. And then Bertram Boltwood in 1907 would be the first person to use this radioactivity to figure out how old a rock is. Bertram Boltwood would tragically go on to commit suicide. He suffered from severe depression, and despite being just an incredible geologist, he was depressed, and so he unfortunately tragically killed himself. Marie Curie's husband would die at a relatively young age, and she just mourned for him her entire life. But Marie Curie is even maybe more awesome than you think, and most people think she's pretty awesome because she is. But during World War One, Marie Curie used her knowledge of radioactivity and radiation to build mobile X-ray trucks. No one would teach her automobile mechanics, so she taught herself and then engineered these mobile X-ray trucks to go onto the battlefields of World War One so that they could X-ray wounded soldiers to help with their treatment. Imagine, how absolutely useful that was and how many lives she saved. She took her daughter. This is her daughter. Helped her with it, and they recruited a whole bunch of nurses and women to drive these trucks onto the battlefields of World War One. And I mean, that's not, without risk. In fact, it's with a lot of risk. But she did. She would die late in life from, yes, radiation poisoning. At the time, they didn't really understand that you really ought not carry, uranium around in your pocket to warm your hands in the winter. And so, yeah, but she really was just incredible. And then later on, Claire Patterson and George Tilton would use the Diablo Canyon meteorite to begin to arrive at a date for the for the age of the Earth, right? Because it's nice to know how old that rock is and how old that rock is, et cetera, et cetera. But the real interesting question here. Sorry, I needed water. The real interesting question, right, is how old is the Earth, right? And so Barringer Crater out in Arizona. The crater itself is about 50,000 years old. But the Diablo Canyon meteorite that made that crater is about 4.5 billion years old, right? And that date was determined by Claire Patterson and George Tilton. And it really was just an amazing exercise in laboratory technique. Right, here's the apparatus that they used to determine because and I actually I don't mean to date myself overly much, but I ran a line like that once in graduate school, and oh my gosh, it was insane. But it wasn't that long ago, so yeah. early 2000s. But anyway, but yeah, right, it was an amazing thing, and they dated this Diablo Canyon meteorite at about 4.5 billion years old, right? So how do you do this? How do you do this radiometric dating thing? Well, okay, so first thing we need to know is what's an atom like, right? What's the structure of an atom? Okay, so protons, neutrons, electrons, right? We all probably know that. I mean, you all took, I don't know, middle school, high school chemistry, right? Protons located in the nucleus of the atom, that determines the element. Neutrons, all right. Sorry, let me say this and make this clear. Right, the number of protons is the element. If it has one proton, it's hydrogen. If it has two, it's not hydrogen anymore. It's helium. Okay, has three, it's lithium. Has four, it's boron, etc., etc., etc. Okay, the number of protons determine what the element is. So if you change the number of protons, you change the element. Let me jump to electrons next, because everyone knows about these too, right? Electrons move around the nucleus of the atom very fast, and they determine the charge, right? Electrons are negatively charged. Protons are positively charged. So if you take away an electron, the charge goes positive. If you add electrons, the charge goes negative. Okay, I say move very fast, but I think I talked about this before. When you think about atoms, don't think about electrons moving around the nucleus like a planet moving around the sun, right? Even if it's only one electron, it's very small. It's moving very near the speed of light. It's moving very near the speed of light over a very small area, which means that even one electron is effectively a cloud around that proton. Okay, now the great neglected subatomic particle is neutrons. Neutrons are located in the nucleus of the atom. They determine what we call the isotope. Okay, you can change the number of neutrons in the nucleus of the atom, and what you do is you change what's called the isotope. For example, presumably you're breathing right now. Don't hold your breath. Okay, so you're breathing an atmosphere that is mostly nitrogen, right? But about 20% oxygen. Now, as you breathe that oxygen, you are breathing two isotopes of oxygen. Some of the oxygen you're breathing has 8 neutrons. We call that O16. Add the 8 neutrons with the 8 protons, that makes it oxygen, and you get 16 O16. But some of the oxygen you're breathing has 10 neutrons. That is a different isotope of oxygen. Okay, we call that isotope O18. Okay, so add the 10 neutrons to the 8 protons, you get 18 O18. So you are currently breathing 2 different isotopes of oxygen. Okay, and your body does not care. They are chemically identical. Okay, now they're physically different. The O18 is a little bit heavier than the O16. And that is something that we can use to do all kinds of things in geology. And, I took a whole class in what are called stable isotopes, because those are stable isotopes. And stable isotopes are incredibly useful in a number of different ways that we do not have time to go into. If you're interested in stable isotopes, ask me. I'll do a thing, but they are very useful, but they're not useful for dating. Okay, so here's the idea, right? So you got these 3 things. Now, O16 and O18 are stable isotopes, but not every isotope is stable. Some combinations of protons and neutrons simply do not play well together. They're not going to stick around. Okay, and so what's going to happen is that unstable isotope that we will call the parent is going to emit subatomic particles, various different kinds, because there's various different kinds of radioactive decay, but it's going to emit subatomic particles, and it is going to turn into something else. Okay, so for example, An unstable isotope of carbon turns into nitrogen. An unstable isotope of uranium turns into lead. An unstable isotope of potassium turns into argon. Okay, there's all of these different unstable isotopes that will turn into something else. Okay, now they do this according to something that we call a half-life. A half-life is the time that it takes for half of the unstable parent isotope to turn into a stable daughter product. So let's take a look at how this works with a graph. Okay, so here we have time equals 0. Okay, so and what I have here is the percent of the parent isotope. So this is the unstable isotope, right? At the beginning, you have 100% of that parent isotope, which brings us to the question, when is the beginning? Right? When does this radiometric clock start? Okay? It starts when the igneous rock cools. That's when it starts. Okay, so this technique works best on igneous rocks. Now, you can use certain minerals that are very, very resistant to change and very, very resistant to all kinds of things to date things with. But if you want to date the rock, you probably almost certainly need to be dealing with igneous rock. Okay, once that igneous rock cools below what's called a barrier temperature, it's now a closed system, and the only place that daughter product can come from is that parent. So that gives us a technique, right? So when that igneous rock cools, bang, tick, 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 tick. Now the radioactive clock is ticking. Okay, so at the beginning you have 100% parent. Okay, after one half-life, 50% of that parent has turned into daughter, and now you have 50-50. Now, after two half-lives, you don't lose the other half. You lose half of what you have left, right? So after two half-lives, you're down to 25% parent. Right? See, now once again, what you do in the next half-life is you lose half of that 25%. So now you're down to 12.5% of the parent that you had left, and then after that you're down to 6.25, and now you're down to 3, and etc. And we can draw a line through it so we can know what's going on in between these two, right? And if we were really fancy, we would put the formula for this line, but we're not that fancy. Okay, so you use an instrument called a mass spectrometer. Right, and you stick your mineral in it, and you tune it properly, tell it what isotopes to look for, and then what it's going to do is it is going to tell you how much parent you have and how much daughter you have, right? And that will tell you how many half-lives have gone by, right? So you stick it in there, and it says, okay, you've got 25% parent, 75% daughter. That's 2 half-lives. Or maybe it says you've got 12.5% parent and, however much daughter, right? So that's 3 half-lives, right? Maybe it says you got 50-50. That's 4 half-lives. Or 1 half-life, sorry. Okay. Or maybe it says you got, here. You've got, went too far. Hold on. Here we go. So maybe it says you got, I don't know, you've got, what would that be? That would be 30%, 70, right? So now maybe you're at about 1.5, right? So, so it tells you, based on the percent of parent and the percent daughter, how many half-lives have gone by, right? The more parent you have, the fewer half-lives have gone by, right? Eventually, you get out here, and it just doesn't work anymore because you're basically out of parent. Okay, so you hand the geologist a rock. You say, how old is this rock? And they say, let me put it in my mass spectrometer, right? And they do, and they give it back to you and say 3 half-lives. Well, that's not helpful. I mean, that's not even as helpful as Lower Cambrian, right? So okay, so great. We know how many half-lives have gone by. How old is the rock? Well, there's how long half-lives are for various and sundry common radiometric unstable isotopes, right? If you're using uranium-238, and it has a half-life of 4.5 billion years. Okay, that is just coincidentally the age of the Earth, right? And so even the oldest rock on the planet, is 50% uranium-238, 50% lead-206, which gives us one half-life, and that's 4.5 billion years old, right? If on the other hand, maybe you're using uranium-235, that only has a half-life of 713 million years old, right? And so maybe you tune it for uranium-235, and sorry, man, I keep doing that, don't I? You tune it for uranium-235, right? And it comes back, and the guy says, okay, it's two half-lives. Well, 2 times the length of a half-life, 713, means that it's 1.4 billion and a little older, 1.4 billion years old, right? I'm sorry, 713 million times 2. Okay, and I'm too tired to do math in my head. But anyway, no, that's 1.4 billion years old, right? So that's what you do, right? You figure out how many half-lives have gone by using the ratio of parent to daughter isotope, and then multiply the number of half-lives by the length of a half-life. Pretty dang easy, really. Now, in reality, it's difficult, okay, because you got contamination issues, you got all kinds of things. It's not just automatic, stick it in a mass spec and spits out a number. It does not work that way. You might have heard of carbon dating. Archaeologists do a lot of carbon dating. Carbon has a half-life of about 5,730 years, right? And so carbon works really well on things that are only a few thousand years old. If I put my 300 million year old rock in a mass spectrometer and tune it for carbon 14, there's no carbon 14 left. It's all gone, right? So which isotope you use depends heavily on how old you suspect the rock is. If you suspect it's really old, use uranium-238. If you're an archaeologist, you have no use for uranium-238. You're going to use carbon. If you're me, I'm using uranium-235 because most of my stuff is a few 100 million years old, right? Yeah, tune your mass spec for how old you suspect the rock is, right? And so there's a mass spectrometer. If you really want to know how one works, ask me and I'll tell you. So the radiometric clock starts when the igneous rock cools, right? Determine the ratio of parent to daughter isotope. Right? Is it 50-50, 25-75, whatever, right? Determine where you are along this curve, right? Once you know that, use that to determine how many half-lives have passed. If your ratio is here, go down 1.5 half-lives. If your ratio is maybe here, go down 2.8 half-lives or whatever, right? Determine how many half-lives have gone by. And then multiply the number of half-lives by the length of a half-life. Bingo. There you go. That's how old the rock is. Okay? Like I said, it's harder than that, but that's the basics of it. Now, this really works best on igneous rocks. It really, truly does. But the good news is, let me just show you this. There's more igneous rock around than you think. This is one of my coals. That thing running right through the middle of it, that's an ash layer. So I can chip that off, send it to a friend of mine who has a mass spectrometer. She can tell me how old that rock is. Well, if that ash layer is however old that is, that coal is that age too, right? It's right in the middle of that coal. So I can look at the fossils in that coal, tell how old they are, and now when I find those fossils somewhere else, maybe without the ash layer, now I still know how old that coal is because I know how old it is there, assuming they have the same fossils, right? And so, yeah, there's a lot of ash out there. There's a lot of igneous rock out there, and if you do it enough, you can start to bracket things in, and you can start to tell the dates of even sedimentary rocks based on the igneous rocks around them, right? So yeah, it works out really well. So let me show you one more thing, and then I'm done. And that is, I want to go back to this. And in particular, let's think about this batholith, that dike complex, and that sill. Or rather, dike, sorry. I'm really tired. That batholith, that dike sill complex, and that dike, right? So, common sense tells us This cuts that, so this is younger than that, right? Common sense tells us this cuts that, so this is younger than that, right? So this is the oldest, this is the youngest, this is the younger. I'm sorry, let me say that again. This is the oldest, this is younger, this is the youngest, right? Now, those are igneous rocks. We can radiometrically date them. And every single time we do, the radiometric dates confirm our common sense cross-cutting relationship dates. Look, there are people out there who don't want radiometric dating to work because they want the Earth to be 6,000 years old and the radiometric date for the Earth is 4.5 billion, right? So they're coming with all kinds of weird reasons why radiometric dating doesn't work, but it does, right? You are never going to find this cutting this and this coming out with a younger radiometric date than that does. It never happens. It just doesn't happen. We also use, we understand radioactivity, right? We build nuclear reactors. We use radiometric tracers in medicine all the time. We know how this works. We would need to be so very wrong about so many things, and we're just not that wrong. I'm always willing to accept that there's things that scientists don't know, absolutely, but this is not one of them. We really, it's relatively straightforward. We have a pretty good idea about how this works, and like I said, it's not just one rock. It's thousands of rocks, and it's rocks overlapping each other where we can work out the common sense cross-cutting relationship, and then do the radiometric work, and it matches up. It absolutely matches up. So that's what I'm going to leave you with. And so I'm going to go get this up on YouTube, and we will move on next time to talking about rock deformation. And so yes, okay. Hope you all enjoyed, and have a good evening, day, or whatever when you're watching. Take care. Bye bye.